Okay, so still continuing number 9, so part 2. And I just went ahead and I wrote down what we had so far. So we obtained our the very first video we had our eigenvalue, which was 4i, and we went ahead and substituted it into our characteristic equation to obtain an eigenvector, right, which has complex entries, right? This is really plus, again, 0i. I called it xy. The book calls it ab. Choose your preference. It doesn't matter. If you want to choose ab, that's fine. And in the very first video of number 9, so let me go ahead and write something down. So I think I said I was thinking of real roots, but when you work with real roots, distinct real roots, case 1, if lambda was 4, for example, then you would find the associated vector. I think I did it in number 2, and then the other eigenvalue, then, case 2, you'd substitute that guy in, and then you get a different eigenvector. But when you work with complex numbers, you really only have to choose one of them, and I chose a positive one because remember we found out that our system was it had infinitely many solutions, so the points are really on the same line. The lines are in disguise, but they're really the same line. The reason we don't need to worry about this one when you have complex eigenvalues is because we're assuming that the matrix A has only real entries, right? Our matrix A, I forgot what our matrix A was already, but the entries were only real numbers, and so if we have, okay, I forgot what this guy was, but they're real entries. If you take the conjugate of a matrix with real entries, you're going to get the same thing. So we know this guy is the same. If you take the identity matrix and you take the conjugate of an identity matrix, well, the conjugate of 1 is 1 because 1 plus 0i, okay, 1 minus 0i. So it's really the same. So that's where we only need to work with one complex solution because, obviously complex numbers come in conjugate pairs, and they both have to satisfy our system that we need, and we have a real part and we have an imaginary part, and it works out nicely. We actually like when we get complex solutions. It gets a little ugly, but in the end, it's actually very nice. Okay, so complex eigenvalues. So we want to find our solution. So this is x of t equals, so v e to the lambda t. Now, if you notice in theorem 1, right, this is a piece of a solution, right? It was like c1 v1 e to the lambda 1 t. But again, we're only using one lambda here. This is our bold vector. And here, because our lambda, right, is a complex number, I'm going to go ahead and call it alpha plus beta I, right? I think the book uses p plus qi. I'm used to alpha and beta, but again, choose your preference. T. Okay, so I use this guy. And remember, what is our v? Well, our v is right above, right? Here is our v right here. It's 5 and 2 minus 4i. So here's 5, 2 minus 4i. And if you look in your book, I think it's equation 20 on page 374. They kind of generalize it. They have this, a1 plus b1i, a2 plus b2i, all the way to an plus b and I, right? This is, our n is 2, so this is really what we have. Okay, but we can, if we want to, we can split this guy up, right? This really means to make it look like 20. So 5, 2, right? That's our, our whole A, our big A, because that's it's a vector. And plus, right, our imaginary parts. We can say 0, negative 4, I, right? This guy is our vector B. Let's just be careful. Let's write it a little bit nicer. So A. So that's what they mean by equation 20. Okay, so hopefully this makes sense. This is what I'm going to use. So let's go ahead and, just work this out. Okay, so we have, so I just wanted to write a couple of those things down to kind of explain what that page was talking about. Okay, so let me make this a little bit bigger. Okay, so we have x of t equals, okay, so we have our, let's write our vector. I'm going to write it like this. So I have 5 and 2 minus 4i. Okay, and then I have, so there's my v. Okay, e to the alpha plus beta I. Well, what's our alpha? Remember, lambda was, right, it's really 0 plus 4i. So there's your alpha and there's your beta, or if you want to call it p and q. So alpha is 0 and beta is 4. Yes, it's 4. And I'm not sure if you guys remember Euler's formula, which with complex numbers is, it's e to the, well, let's go ahead and write it out. It's e to the alpha, and it's cosine of alpha t plus I sine beta t. You might have seen this in maybe a trig class or pre-calculus class. So it's just another way of writing a complex number. And let's see, just make sure I didn't forget anything. Okay, so now let's insert a few things. Okay, so here's my a and b, so just rewrite this. That's a 2 minus 4i. Okay, e to the alpha. Well, alpha is 0. So, I mean, this guy is really e to the 0, which is just 1. So, again, this is just a big 1, so I don't need to write it. And let's insert our cosine of, oh, and I actually have to be a little careful here. This is not alpha, this is beta. Otherwise, we will get the wrong answer. So, okay, let's maybe put it in color. So this should be beta, right? And this one's okay. So beta and beta. And we have cosine of beta, which is 4. So cosine of 4t plus I sine of 4t. Okay, so hopefully you guys can see, I mean, we have our 2 by 1 vector times this value. And again, when you have complex eigenvalues, you should have cosines and sines within your expression. And I mean, this is basically it, but we can't stop here. We can definitely simplify this using, 5.3, right? Some scalar multiplication, combining some like terms, so you can match the back of your book answer. So I'm gonna go ahead and stop here again because I think the last video was 14 minutes and it took forever to upload. And the next video should be the last video for number 9. So that's gonna be ... We're basically gonna simplify this guy. Okay, see you in the next video.